space-field contraction and expanse-field motion. By balancing these two, the ship is squeezed forward. Because the ship is effectively stationary within its own local pocket of space, it doesn't experience the g-forces or mass resistance of standard Newtonian acceleration, rejecting the mass limit. In your view, and in extended classical mechanics, the limit isn't about mass becoming infinite. Instead, it's about energy partitioning. The theory: as an object approaches light speed, the energy being pumped into it is split between translational motion, speed, and intrinsic field dynamics, the energy required to maintain the object's existence against the background expanse. The result: you don't hit a mass wall, you hit an equilibrium point where the self-generated acceleration of your field is perfectly balanced by the counteraction of the universe's background expansion. Direction of expanse as the fuel. If we treat the expansion of the universe as a directional vector, we can align our ship.
In December 2025, a new peer-reviewed study revisited the physics behind warp drives and proposed a refined theoretical design that better fits the equations of general relativity. The research does not claim faster than light travel is achievable today, but it does show that warp geometries can be structured in more realistic and stable ways than previously assumed. By reorganizing how space-time distortion is distributed around a spacecraft, the study reduces some of the most extreme assumptions found in earlier models. In this video, we will examine what was proposed, why it matters scientifically, and what remains unsolved. Let's get started. Warp travel became a serious topic in physics in 1994, when physicist Miguel Alcubierre demonstrated that Einstein's equations allow a space-time configuration capable of producing effective faster-than-light motion. The key idea was that a spacecraft would not move through space faster than light. Instead, space itself would be reshaped, compressed ahead of the craft and expanded behind it. Within this space-time distortion, the spacecraft remains locally stationary and never violates relativity. The difficulty was never mathematical consistency. It was physical feasibility. Alcubierre's original warp bubble required enormous quantities of negative energy, an exotic form of energy that classical physics does not permit. While quantum effects can produce extremely small and temporary negative energy densities, nothing known can generate them at meaningful scales. The new study, led by physicist Harold Sonny White and published in Classical and Quantum Gravity, does not eliminate this requirement. What it does instead is rethink the structure of the warp field itself. Rather than enclosing the spacecraft inside a single continuous spherical warp bubble, the proposed design distributes space-time distortion across multiple discrete regions. These regions are described mathematically as Gaussian cylinders and are positioned away from the main body of the spacecraft. This configuration allows the spacecraft interior to remain in a comparatively flat and stable space-time region, while the extreme curvature required for warp motion is handled externally. In practical terms, the most intense space-time manipulation is shifted away from the vehicle itself. The study shows that warp effects do not require one rigid geometry. SPAC-IME distortion can be modular, directional, and separated into functional regions. This reduces sharp curvature gradients near the spacecraft and improves theoretical stability. The negative energy requirement is still present, but it is no longer spread across an entire enclosing shell. Instead, it is localized to specific regions, making the model easier to analyze and compare against alternatives. The central contribution of the study is not a workable engine design, but a demonstration that warp metrics are more flexible than previously assumed. Within general relativity, there is more than one way to shape spacetime for warp-like motion. That flexibility is the discovery. The significance of this research lies less in propulsion and more in fundamental physics. Warp metrics act as stress tests for general relativity. They push Einstein's equations into extreme regimes where spacetime curvature behaves in unfamiliar ways. Studying these solutions helps physicists understand where the theory remains consistent and where deeper problems emerge. For decades, discussion of warp travel focused almost exclusively on the Alcubierre bubble. This created the impression that warp motion required a single massive spacetime distortion surrounding a spacecraft. The new study challenges that assumption by showing that similar effects can be achieved using separated spacetime regions. This has theoretical consequences. It expands the range of allowable spacetime topologies and demonstrates that warp-like behavior is not tied to one specific shape. That in turn allows physicists to explore trade-offs between stability, energy distribution, and curvature intensity. Another important contribution is conceptual clarity around exotic energy. Earlier models treated negative energy as a uniform requirement across large volumes of space. This study confines it to specific structures, sharpening the question of where classical physics fails and why. This does not make negative energy easier to obtain, but it makes its role more precise. When theoretical obstacles are clearly localized, they become easier to analyze and harder to ignore. The work also highlights an interesting convergence between speculative design and physical constraints. Separating high-stress spacetime regions from the spacecraft interior mirrors basic engineering principles. Even though this work operates at a purely theoretical level, at the same time the study reinforces existing limits. The need for negative energy implies violations of classical energy conditions, which remain one of the deepest unresolved issues in theoretical physics. These are not technical details that can be engineered away. They point to gaps in our understanding of spacetime and vacuum energy. Alternative warp concepts exist, including models that avoid exotic matter by accepting lower speeds or extreme energy costs. So far, none offer a clean solution that preserves both physical realism and usefulness. In this context, the study does not overturn prior conclusions. It refines them. It narrows uncertainty by showing which assumptions can change and which cannot. That is why the work is taken seriously within the field. The immediate impact of this research is conceptual rather than practical. By introducing a modular warp geometry, the study provides a clearer framework for future analysis. Segmented spacetime structures are easier to simulate, test for stability, and compare across different theoretical models. This allows for systematic exploration rather than isolated thought experiments. The work also improves understanding of how spacetime responds to extreme curvature, even if warp travel remains impossible. Insights gained from these studies inform other areas of physics, including black hole dynamics and early universe cosmology. However, the central obstacle remains unchanged. Negative energy is still required, and no known physical process can produce it in the necessary quantities. Until that problem is addressed, warp drives will remain mathematical constructs. Future research is likely to focus on three directions. First, continued optimization of warp geometries to minimize exotic energy requirements. Even incremental reductions help clarify whether current limits are absolute or contingent. Second, deeper investigation into quantum vacuum behavior. While current quantum effects are far too weak, understanding how vacuum energy behaves under extreme conditions may reveal new theoretical constraints or possibilities. Third, experimental efforts aimed at precision measurements of spacetime and vacuum effects. These would not test warp drives directly, but they could inform the underlying physics that warp concepts rely on. Warp research today occupies a familiar position in science. It is mathematically consistent, physically unresolved, and technologically unreachable. Similar positions were once occupied by black holes and gravitational waves long before observational tools caught up. Whether warp travel will follow that trajectory is unknown. What is clear is that each refinement sharpens our understanding of spacetime, even if practical applications never emerge. This study doesn't make warp travel possible, but it refines what physics actually allows. Negative energy remains the unsolved barrier, keeping warp drives theoretical for now. Even so, the work sharpens our understanding of spacetime at its most extreme. As the discussion moves forward, it becomes important to place this research within the broader context of how theoretical physics progresses. Ideas like warp drives exist at the boundary between established theory and speculation, where mathematics allows certain solutions but nature has not yet revealed whether they can exist physically. In this sense, the refined warp geometries proposed in this study function as conceptual probes rather than blueprints. They help clarify which aspects of Einstein's equations are rigid and which remain open to reinterpretation under extreme conditions. This distinction is critical because it prevents speculation from drifting into misconception while still allowing creative exploration within well-defined limits. One of the most valuable outcomes of this work is how it reframes failure. The persistence of the negative energy requirement is not simply a setback. It is a precise signal pointing toward unresolved physics. Energy conditions have long been used as guiding principles in general relativity, but they are known to be violated in subtle ways by quantum effects. By narrowing where and how these violations would need to occur, warp research sharpens the interface between gravity and quantum theory. That interface is already central to modern physics, appearing in problems such as black hole evaporation, vacuum fluctuations, and the structure of spacetime at the smallest scales. This is why studies like this continue to attract attention despite their impracticality. They do not promise near-term propulsion breakthroughs, but they force consistency checks across multiple areas of theory. Any future framework that successfully unifies gravity with quantum mechanics will have to explain whether configurations like modular warp geometries are forbidden, permitted, or transformed into something entirely different. In that sense, warp metrics act as benchmarks for future theories, testing their internal logic under extreme demands. For now, warp drives remain tools for thought rather than engineering. They help map the outer boundaries of what current physics can describe without contradiction. Each refinement removes unnecessary assumptions and exposes the true obstacles more clearly. Whether or not spacetime can ever be shaped for practical travel, the process of asking these questions deepens our understanding of the universe. Progress here is measured not in speed or distance, but in clarity. That clarity is what ultimately drives science forward, even when the destination remains far beyond reach. Thanks for watching. Subscribe for new updates and press the bell icon.
You unlock this door with the key of imagination. Beyond it is another dimension. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone.